Welcome everyone. I am Marie and with Carrie Mazoum from the French Competence Center. We are part of the EuroCC project. And with Pierre Aubert from the lab in Annecy, together we organize the Grey Scott Birthdays and the Grey Scott School, which is now only about 1 month away. So this is really the moment to register. We are very happy to announce that several new satellite sites have recently joined the adventure across different European countries, meaning even more opportunities to follow the school locally with colleagues and local communities. If you like the full immersive experience, there are still some places available in Annecy to spend the 2 intensive weeks directly with the teachers and other participants. And we even have solutions and contacts to help with accommodation if needed. So don't hesitate to reach out quickly. And as a reminder, the school is very flexible. You can attend the full program, register for only a few selected days, follow from one of our satellite sites across Europe, or join fully online. I will share all the useful registration links in the chat very soon. And of course, if you enjoy these webinars, please continue spreading the word around you. Every share, comment, or LinkedIn post really helps us grow this HPC community.
Could a simple chemical reaction teach you how to unlock peak performance on today's supercomputers? Welcome to the Grey Scott School 2026, a free, advanced summer school on high-performance computing. Designed for professionals from industry, public sector organizations, and academia. From June 22nd to July 3rd, 2026, join us in Annecy, France at LAP, at one of our satellite sites across Europe, or online via live streaming. All courses are taught in English. You can pick the courses most relevant to you or dive into the full 2-week program. You'll learn the practical behavior of modern hardware and how to write performance-optimized portable code. Week 1 focuses on CPUs, Week 2 on GPUs, covering architecture, bottlenecks, parallelism, memory, and performance analysis. All learning is built around a single challenge: simulating the Grey Scott reaction. Simple to start, yet complex enough to stress compilers and expose performance limits. You'll explore modern tools, languages, and libraries such as C++ 17 and 20, CUDA, Fortran, Python, OpenMP, TBB, Kokkos, PyTorch, and more. The school provides ready-to-use container environments for smooth hands-on sessions. Expert instructors from CNRS and CEA guide you with live Q&A and community support on Discord. Satellite sites let you learn together locally without traveling. Want to host one? It's easy with our turnkey setup, sharing the school with your colleagues and ecosystem. You'll leave not only with hands-on HPC skills, but also an official certificate of participation. And you know what? You can start early with 18 Grey Scott Thursdays webinars, weekly from January 29th to June 11th, introducing summer school concepts and new topics. Whether you're an industry professional, engineer, researcher, or student, if you have programming experience and want to push your skills further, this program is for you. Register now at cc-fr.eu and start learning today. Grey Scott School 2026, Europe's leading HPC summer school.
So now, today's webinar is dedicated to Kokkos on GPU and will be presented by Yuichi Asahi and Paul Zehner from Maison de la Simulation, and I will let Pierre introduce them. Pierre, it's up to you.
Okay, thank you, Mary, for the nice introduction. So yeah, today we will do some magic on GPU with Kokkos. So the second part of the webinar of Kokkos you already follow, I believe, at some point. We'll have Yuiki and Paul. So Yuiki is working. So both are working in Maison de la Simulation at CEA, so near from Paris, and they both work on a lot of fluid simulation and plasma simulation, because of course that's the purpose of CEA at this point. So it's quite normal. So big simulation. So you see that GPU are very involved in this kind of simulation. That's why, of course, they use Kokkos and they try to push it in the maximum. So today we will have a first presentation of Yuiki about how to add F50s in Kokkos with GPU, so how to extend the functionalities of Kokkos. And then we will have feedback about some computing using Kokkos on GPU by Paul, so on a real use case application. Of course, if you have some questions, as always, try to write them in the chat. We will answer all the questions at the end of the session. And without further ado, I will give the floor to Yuiki to present you the F50 on GPU with Kokkos. Yuiki, it's up to you.
Thank you, Pierre and Marie, for the introduction. This is Yuichi Asahi from Maison de la Simulation. I'll talk about the recent development of the F50 interface for Kokkos ecosystem called Kokkos F50 for the performance portable solution for F50. This work is mainly done by the Maison de la Simulation with my colleagues like Travis and Tomer and Julian. The support from the CUDA team, which is the exascale, the preparation project for the exascale supercomputing in CEA. And as a part of this project, we developed this library. This is the introduction of my talk. And firstly, I talk about the where do we need the F50s, and then talk a little bit about the Kokkos ecosystem and its existence of the F50 libraries. What's that? And we go over the performance portable solution for distributed F50s and the introduction of the F50, Kokkos F50 itself, and its extension to distributed port. And then talk a bit about the benchmarking using the 3D-dimensional, the Navier-Stokes equation solver, and summarize the talk today. Let's move on to the introduction. So where do we need distributed F50s? There are a couple of fundamental use cases for that. On the left top, this is three-dimensional fluid simulations. And this is typically it's a direct numerical simulation, and we often employ the periodic boundary conditions where the distributed F50s are essential for good performance. Actually, I myself is contributing to developing the plasma turbulence simulation code for nuclear fusion, and this is application developed by CEA and ERFM, and this one is also using F50s because in the for plasmas, and this type of plasmas, we have the fundamental periodicity along the toroidal direction, so we can certainly use F50s for that. Another big user is the molecular dynamics simulations. The most famous one is RAMS, and they are using the F50-based particle mesh method, and so distributed F50s are also useful for them. Of course, we need a performance portable solution for distributed F50s, because in GPUs can be offered by different vendors like NVIDIA or AMD or Intel. Of course, we need good scalability for that. In this year, we are at the preparation for the exascale systems like Jupyter and NVIDIA machine in Germany, or Frontier and US and the AMD machine, and the Aurora and the PVC from Intel. At first, we are considering there are many different options like directives like OpenCC or OpenMP, or higher level abstraction like Kokkos or Sycl. And among these, we choose Kokkos in the end. There are two fundamental reasons for that. Kokkos has its own ecosystem, and it's also under HPSF, which is I will come back to this point later, but its HPSF is under Linux Foundation, and it's kind of ensures better sustainability compared to other frameworks. So we choose Kokkos for that purpose. When it comes to the existing distributed F50 libraries, there are a couple of options available, most likely on open source. One example is the 2D comp and F50 library. It's between Fortran and OpenCC. It offers CPU and NVIDIA GPU solution. A CUDA comp and CUDA F50MP are offered by NVIDIA, Of course, it only works with NVIDIA GPUs, but it works quite nicely with NVIDIA GPUs. To the best of my knowledge, the only library that offers performance portability is the HEA50, which implements the certain kernels in CUDA and heap and Sycl to offer the vendor neutral solution. In short, distributed FFT libraries consisting of FFT port, and most likely it is their areas to the vendor FFT libraries, because vendor offers the optimized libraries. And also for the communication port, most likely with MPIs, or can be more for some libraries, and also for transpose kernels, because when the transpose kernels are basically between their solution, like the CUDA or heap or Sycl, HEA50 need to write in their repository, they need to write NVIDIA solution CUDA in CUDA, and also for the heap and also for the Sycl by themselves. Our approach is quite different. We make it on top of Kokkos ecosystem, like Kokkos and Kokkos FFT, to get performance portability roughly for free. We offer the CPU and GPU solutions just using Kokkos, so our kernels are fully performance portable. And another nice perk is that in the Kokkos offers the quite nice data structure, not only for performance portability, but for the data structure like views, which allows us to program quite easier, and also for safer. And also it offers the consistent build system. So our solution is much more synergy with the Kokkos application, because it natively supports Kokkos build system, so you don't have anything to do to write your own CMake to support HEA50, which is necessary if you like to use Kokkos and HEA50 at the same time. Kokkos actually is the HPSF project. So HPSF is under Linux Foundation for the high-performance software solution. It promises performance and portability and productivity. The key idea is it is open source software project, and it's vendor neutral. And another important aspect of Kokkos is that Kokkos has its own ecosystem. For linear algebra, Kokkos has Kokkos kernels. For FFT, Kokkos FFT, and for communication, it has Kokkos.com, and for performance tooling, it has Kokkos tools. So it has its own ecosystem, which is a unique feature compared to other programming models, performance portable programming models. The Kokkos key features is a single code runs everywhere, and the Kokkos build offers the multi-dimensional array support, accessible from CPUs and GPUs, and the Kokkos offers parallelization for multiple patterns like for and reduce and scan. Is also operated on CPUs and GPUs. As the same principle works for Kokkos 50, the single code runs everywhere at the same time. So we now move on to the distributed 50 port. So firstly, I'd like to let you know why Kokkos 50 and who needs it. As I said, we are the one who need it. We are developing the Zehner application for plasma turbulence with a periodic along this direction, so we can safely use A50 for that direction. The Kokkos A50 target the people who write code of legacy application which relies on A50 libraries. For example, the free simulation codes with periodic boundaries or plasma turbulence. We may also target somebody who has already a Kokkos code and waiting to integrate some in-situ data processing with A50s, something like spectral analysis or low-pass filter, for example. For those who would not like willing to get through the documentation of the fact standard A50 libraries, still want to benefit from powerful A50 libraries, just as simple as NumPy A50. This is the key design of the Kokkos A50. As you can find that here, and the snippets from the bottom, and here their APIs are slightly different. And for example, A50W offers this one, and Rock A50 offers this, Nuke A50 offers this, and YMK is slightly different. Each time you need to carefully read the documentation, and you need to understand how it works, and it's kind of time-consuming procedure if you just like to use vendor libraries. Our solution is much simpler. You can just imagine NumPy 50, and we have the same interface, roughly same interface, which is Kokkosified in the sense that you also take the execution space and you also take the input and output, compared to the output is return type in the NumPy 50. But roughly the same interface, you can safely use it if you know the NumPy 50. The whole details between Joss paper and 2025. So we recently released the Kokkos 50 version 0.1.1, and the key concept is as simple as NumPy as first as vendor libraries. We support 1D to 3D 50s over 1D to 80 Kokkos views. And the APIs are quite simple, and view is all we need, and no need to access the complicated 50 APIs. You don't need to read the vendor documentations. It's much safer API at the same time because we don't allow users to manipulate raw pointers directly. And we also have the compile time and runtime checks for invalid usage, just like in the you are using the 50 libraries for GPU or the host data, which doesn't make any sense. And this is issues compile error. For supporting multiple CPU and GPU backends, for CPUs we have the serial and threads and OpenMP backend. For GPUs we have the CUDA and heap and Sycl backends. And effective libraries dedicated to the Kokkos backends are automatically enabled. We also support the base data type of Kokkos. You can use either layout left and layout right, and you can also use default execution space and default host execution space. If you enable it, you can also use Kokkos serial execution space. At recently, there are some internal use cases, like in DDC, developed by Padioleau, and also for the Zehner, and it's a fundamental library for the Zehner code now, and it's developed by Emily, and these libraries are using Kokkos 50 internally. Key difference compared to the NumPy interface is that in the reusable F50 plans, as you may know, it is actually more costly to construct F50 plans rather than executing F50 libraries, particularly for Q50 and Rock50. So we'd like to construct plan once, and we'd like to reuse plans. So in this example, we constructed F50 plans on top of the X and X hat, and because in the Y and Y hat has exactly the same data type and extents, we can reuse the same plan for the Y data type. However, if you cannot use it for the Z because it has different extents, so you need a different plan for that. In this case, you get a runtime error because inconsistent extents. So it is still safe to use, but indeed we can reuse F50 plans, which is a unique API compared to NumPy. We have kind of the reasonable documentation as hosted on the user docs, and in my opinion, the good part is that you have the copy-pasteable example embedded for API reference. For example, in this case, one-dimensional F50 API, you can have the just copy-paste using copy button, and it can be compiled directly, and you can get the expected output if everything works correctly. And this is compilation is checked at a CI each time, so it is quite maintained all the same time. So it's easier to understand how the API works with this embedded example. Please check out if you haven't already. So with the another demonstration is that in the simpleness compared to the NumPy. We have the benchmark application for solving the two-dimensional Hasegawa-Wakatani solver using the convolution with F50s. We have some small benchmark case. We are actually solving some physical case. The nicest part of NumPy is that everything is offered by the library itself, and it's quite simple to use the define operation. Of course, the NumPy offers very simple solution, but our Kokkos solution is not that complicated compared to it. You can just use Kokkos 50 API and just Kokkos parallel region to perform the convolution in real space and then go back to the real space again. Performance is whatever because it's kind of natural that compared to the Python version and the Kokkos version is of course faster, but the nicest part is that it runs on any different GPUs without any modification. The same code works, and also for the in terms of lines of code compared to the Python version, it's just it's not that different, and it's just 1.5 times longer, but it's not that long. It's not that complicated. Why you get the nice C++ version and which runs on any GPUs. So I'd like to move on to the distributed 50 part. This is the global architecture of our API library. We have this monotonic API, but internally we have this shared plan, which is the embarrassingly parallel version. It's just an alias to Kokkos 50, and this lab and pencil decomposition is one-dimensional and two-dimensional decomposition. And TPL plan means the alias to the vendor native distributed 50 libraries like Q50MP. Internally, we write everything in Kokkos or Kokkos 50. And for communications, we offer MPI solution as a base default, but you can try also for Nico and Rockus and OneCCL solution for each vendor. Another nice feature is the Q50 library support, and Q50MP actually offers a very powerful solution, of course working only for NVIDIA, but it's kind of very useful because of good performance. In short, the distributed 50 library offer doing domain decomposition, something so what we call pencil decomposition, which is the two-dimensional decomposition. In the green cube, what we call G pencil, which means that in the every single data points are available along Z direction, but it's the other direction is distributed, like X and Y. The same for Y pencil in the blue cube, and same for the X pencil. Basically, in distributed 50, you perform a 50 around the dimension, and all the data points are available, and then move on to the another dimension by transposing, and then perform the 50 where the data points are available, and you can go for the Y to X as well. So we have simple API, the same concept as the Kokkos 50, or you can just prepare views, and also for the no need to manipulate raw pointers. And we basically support the voice via MPI as a default for all communications, but crypto communication interface is also internally available, just Nico and Roku and OneCCL. Also, we support TPRs. Currently, we only support Q50MP, but we would like to extend it to the Rocket50 MPI support or CUDA comp as another solution. Our APIs are not that different compared to the shared version and distributed version. The shared version, we can construct a 50 plan from input and output views and specify the 50 direction, and then you can use that plan on the Kokkos views. Distributed A50 has a very similar idea, but slightly different because you need to specify the input and output topology of the MPI. And you also need to specify the MPI communicator, which is most likely just an MPI communication word, but you can use the sub communicator if you have the subspace. And another important difference is that in this plan also handles forward and backward direction, because internally we need to allocate huge amount of buffers. So we like to use this plan as much as possible. So we need to specify the effective direction at the execution time. Internally, we will choose the different plans depending on the MPI topology you gave us. And each data local, and its reside on a specific MPI rank, and the input-output views are just local, and you don't necessarily have the global data, which cannot exist because it cannot be fit in the single GPU. So implementation details, we employ C++ dynamic polymorphism to select 4 distinct internal plan types. The reason is that in we don't know the MPI distribution at compile time, so we need to make it runtime. Internally, shared plan means just an alias to standard Kokkos 50 API, which is no MPI aware, which is embarrassingly part of the case. The slab decomposition, slab plan means the 1D slab decomposition, and pencil plan is 2-dimensional pencil decomposition. The TPR plan is an alias to the vendor native distributed fit libraries like Q50MP. The core routines consisting of the all-to-all, which is handle the MPI communications, all-to-all, and pack and unpack is just in the preparation and for the communication. And after that, we need to unpack the data from the receive buffer. The transpose is just in the in-memory transpose to align the data for 50s. And normalizations are just in the 1Y, and scaling for 50, it's optional. If you don't need it, you can just disable it. So our idea is just in the to make communications as simple as possible and do all the complexity on GPUs, because we have explored this. So this is the MPI wrapper. As you can see, we are just calling the MPI all-to-all on the view data, which is kind of very simple. It's supposed to be the fastest because it's the simplest. Because in normal and the communication are the major bottlenecks if you write your code appropriately. On the other hand, then we'd like to address all the complexity on GPUs. We have the expertise, and this is per kernel internally used, and this has the supporting the same kernel supports 2D to 7D views, and parallelized with the so-called MD range policy. Since then, we are also the developers of Kokkos, and we actually encountered performance issue with MD range policy, and we have recently optimized the MD range policy itself, and where I think many users can benefit from that at the same time. And we by ourselves are benefit from this optimization effort. So we will use the Navier-Stokes equation solver 3-dimensional as a benchmark case, and we are solving some physical case, which is simplest, and we are fixing the problem size to the 1000 to the 3, and the FP64 is used, and we show we have the 12 C2R and this 3 R2C repeated 4 times in the Runge-Kutta steps, because we use fourth order time step method. And we also try the batched implementation, because in the velocity field can be stored in a single 4D view if you stack it. And actually, I will tell you later, we actually didn't get any benefit in terms of performance for the batched case, but I expect that at least for example, in delta F gyrokinetic simulations, which rely heavily on 2-dimensional batch distributed FFTs, we should get some performance benefit as well. At least using batched API, you do not need to use the FFT API for different views. In the left, you need to call multiple times for different velocity field, which is kind of annoying. But you can just stack the data structure into a single view. You can just use this 3D batched API, which simplifies the implementation quite a bit. So this is kind of interesting feature. We performed a strong scaling study for this Navier-Stokes code from 2 nodes to 8 nodes, and for AMD GPUs and NVIDIA GPUs for the CPUs. The x-axis is the number of processes, basically number of GPUs or number of processes for CPUs. And the y-axis is the execution time, the lower is the faster. So, and the ideal scaling is written in the orange line, and the blue is actually the measured curve. As you can see in it's scaled relatively nicely for AMD platform and for CPU platform, but it's not for the NVIDIA GPU because it is already faster compared to the AMD GPU, because the communication is slightly faster. But at the end of the day, we encountered roughly the similar performance for NVIDIA and AMD, because the communication cost is roughly identical, and the other parts are roughly negligible. So this is the breakdown on the performance on the AMD GPU and the NVIDIA GPU and Ice Lake. And the blue card shows the total percentage in the execution time for the all-to-all part. And orange curve is NPAC and UNPAC. And green part is the FFT. And the red part is transpose. And the magenta part is the normalization. As you can see, roughly the same trend for AMD and NVIDIA, but in the for the 64 GPU case, and almost 90% of the costs are coming from the communication. So I think it is kind of the very natural situation when it comes to distributed FFTs on GPUs. The situation is quite different on Ice Lake, because communication is not the serious bottleneck here, and we still have some room to improve the performance for the PAC and UNPAC port, and FFT port, and the transpose port. And actually this measurement is done before we optimize the MD range. So we expect that in the PAC and UNPAC can be improved, or should have been improved a little bit with recent MD range improvement, for particularly on AMD architecture, as well as NVIDIA. The optimization on the CPU port is kind of ongoing. And as you can see, the communication is not the major bottleneck. There's some room to overlap on Ice Lake architecture, which is kind of remains as a future work. We also compare the performance with CUDA-50MP. In this case, we just showed the 16 MPI case and 64 MPI case, and we tried the slab-to-slab slab-to polarization. Firstly, we got roughly the same performance on MI250X and 800 actually for the same for PVC, but in the roughly at the same time, roughly the same performance is obtained for NVIDIA and AMD and Intel. We got a better performance with Q50MP, and this is coming from the usage of NVCMM. But I'd like to emphasize that we initially encountered a problem with Q50MP on 800 machine because of the inappropriate CPU bindings. It's super important to map process needs access to at least 2 CPU cores, because this is a story for I was not expecting this because I was considering only GPUs, but CPU bindings actually matters because of NVCMM restrictions. But if you set carefully, and you get a better performance in Q50MP compared to our implementation, but not much. So our implementation is quite reasonable and works nicely on any GPUs. We also try to discuss a bit about input some topology and batching. Interesting, this is for the 64 MPI case, and the pencil decomposition actually gives the best performance on the 800 machine because of on this machine, and each node has 8 GPUs, which are tightly connected with NVLink, which means that in the one communication cost along one direction is completely negligible. So we have good acceleration for this machine. Actually, which is not the case for Adastra, because we don't have such nice communication layer in Adastra. We don't have the fully connected NVLink-like structure on Adastra, so we cannot have the acceleration on this situation. For the ice flake, we certainly need further optimization needed because the vectorization is a strong issue in the MD range. We recently identified the solution for that, so hopefully this can be addressed quite in the near future. And the batching actually did not help because the hashed part is the batched case, and you can see that almost always the execution time is longer for the batched case on GPUs. But sometimes we got acceleration on the ice flake, but it's not the case for the GPU for the moment. So in this case, we didn't get any benefit in terms of performance using batching, but at least you have the nicer code using batched capability. We are also considering another coming feature in Kokkos 50, which is the batched APIs. When I say batched, it's the highly inspired on the batch and burst wrapback APIs in Kokkos kernels, which I mean that you can call the batched API inside Kokkos kernel like this one. So for example, you can have the batched API under the Kokkos parallel region, which is kind of very interesting feature of Kokkos kernels, and we'd like to also like it and have it in Kokkos 50 as well. This allows us to have the improved data locality, and you can use kernel fusion including FFTs. Of course, it's not as performant as vendor solutions, but it's significantly more flexible, so which can be a very interesting feature. So let me summarize my talk and future work, and we developed the performance solution for distributed 50 in Kokkos ecosystem. And this is safe and simple to use thanks to Kokkos, and good performance on the many GPUs for keeping reasonable performance on CPUs. And we also have the very advanced features like batched capability or vendor native distributed 50 supports. The future work is a better integration of the GPU collective libraries, because communication is the serious bottleneck, and we identify that NVCMM is a better solution, probably LockCMM as well. And the optimization of MD range is ongoing, but we have significantly better version compared to the previous one, and they're mostly done for device and currently ongoing for host. So that's it. Thank you for listening.
Okay, thank you, Yoshi. I think we can move on to Paul, and then we'll answer all the questions at once.
Good morning, everybody. So I would like to propose a kind of different talk for the second half of today's meeting. I sit more on much the practical case of using Kokkos and the Kokkos ecosystem libraries within a CFD solver, which is named Trust. So this presentation reflects mostly the work which has been done by the team of my lab. That's a team that I joined a bit less than 1 year ago. So all the credit is to those people: Pierre Ledac, Rémi Bourgeois, Elie Sycl, Adrien Brunton, and Elie Roumain. So to give the content of my talk, I will discuss a bit what is the context around the Trust CFD solver, how it was accelerated using notably Kokkos, and I would like to show you the efficiency of the acceleration with two consequent simulations that were performed on GPU and also performed on CPU to some extent. So it allows us to give some interesting performance analysis here, and I will conclude at the end. So to start with Trust solver. So Trust is a CFD solver for thermohydraulics, which is developed at CEA by the Energy Division. So it's a code that started in 1993. It simulates incompressible and weakly compressible flows for primarily nuclear applications, but it also diversified its, fields of operation. It can be operated for, say, general non-compressible fluid mechanics. It also used for simulation of fluids of fuel cells. It operates on unstructured meshes. It is coded in C++. I would say C++ between like the 98 norm, 11 norm, 14 norm. It currently uses the C++ 17 norm standard. It's made on 300,000 line of codes. It is parallelized using MPI, and it has a kind of extension mechanism where Trust is the base, as a name of a framework that can be extended by application that we name Baltics. And those Baltics, there is one that I will introduce in the major GPU computations later. Those Baltics are extensions, can be used as plugins to Trust. Trust is also HPC software, so it's flexible as it can run either like from workstations to supercomputers. Simulations that are performed with Trust can range from just a couple of thousand cells to billions of cells, and can span on the execution time from a few minutes to several months of execution. Obviously, a program that's developed from 1993 has been massively developed and optimized with CPUs in mind, but it has been gradually ported to GPUs over the past, say, 10 years. One of the objectives of Trust currently is to run on the future Alice Lecoq exascale supercomputer that will be hosted at CEA, and that should be operational at the end of this year or the beginning of next year. And obviously, this objective, since the Alice Lecoq machine will be mostly on GPU, gives some challenge in order to make this application run as efficiently as possible on the future Alice Lecoq machine. So how we want to tackle this objective? So obviously, we need to accelerate Trust. And for that, we need to define an acceleration strategy. So the idea is to accelerate what is the most time effective. And because the code is, 300,000 lines of code, we cannot accelerate it just in one session. So we have to gradually port the acceleration to GPU of Trust step by steps. And we know that we'll have parts of the code that are not, some subroutines, some kernels that are not necessarily ported to GPU yet. And we have to manage this in computations. So yeah, I was talking about which part of the code we need to accelerate first. Actually, we spend most of the time in the code in the linear algebra solvers that account for 70% of one simulation execution, and 30% in what I name the kernels. So the kernels is the physics, the models, the physics which is modelized by Trust. So all the kernels that basically assemble a very large matrix. And this matrix will be inversed in the linear solvers functions. Obviously, the kernel's part is very specific to Trust. The linear solvers part is a bit less specific to Trust. Trust, historically has some own implementations of linear solvers, but obviously they were developed for CPU in mind. So the idea is, since linear solvers exist as libraries that are already ported to GPU, so the idea is to use those libraries. So we've used AMD Recalculation, NVIDIA MGX, and PETC, which runs on both NVIDIA and AMD GPUs. We also use Kokkos kernels inside of Trust, but this is more recent, and I think in this presentation I don't present simulations that use Kokkos kernels. So this work of using already GPU ported libraries in Trust started as early as 2014. So more than 10 years ago. For the kernels part, so as I said, it's the compute operators, the models that have to be ported to GPU. So here, the modification is larger. As before, we're just using a different linear algebra solver, so it was pretty transparent to the code. Here, we have to rewrite progressively the code. So the initial work of porting the code, the lines of code of the project to a GPU started with OpenMP target programming model. in 2022. This effort was interrupted eventually due to the lack of control that we get over data locality. I can give more details if you're curious about that in the questions. For the current work of acceleration, so the kernels are accelerated using Kokkos. So this port into Kokkos started in 2024. It has been done with the support of SEGSA. So SEGSA is the initiative at the CA level to help porting existing CA code to GPU using Kokkos in the spirit of running on the Alice Koch supercomputer in the next years. So how did we do as a team? So again, I speak for the team of developers that works with me on Trust. So how did we manage to integrate Kokkos on an existing very large enough, I would say, code base? So Trust has a long history of internal mechanics. Trust has its own containers named Trust arrays that were designed before the STL was mature. So the idea that Trust array was modified to encapsulate a device view. So if you remember the course of Thomas Padioleau a couple of weeks ago, the view is the data container in Kokkos. And we have a device view, so data contained on the device, on the GPU, and a host view, so data contains the same data but on the host. And the trust array contains both device and host view. We perform manual Kokkos allocations for now. So this is a bit obscure, but this is not actually the right way to do Kokkos actually, but this is due to historical reason and how OpenMP target was used, and this will be changed in the near future. As I said, we may need to run the code, say a chain of execution of functions, with not all functions being accelerated to GPU. So for the idea, we need to have an synchronization process between the CPU and the GPU. And what we chose is to have an explicit CPU to GPU synchronization process using accessors. For instance, just before starting a kernel that will run on GPU, we request access to a trust array by modes which are read-only access, read-write access, or write-only access. And depending if the data was modified lastly on the GPU or on the CPU, then a data transfer from the CPU to the GPU will be initiated. Reversely, for all the functions that are not yet ported to GPU with Kokkos, we use an implicit GPU to CPU synchronization, meaning that if we need something in a CPU in function with just CPU code, and the data is also on the GPU, then we synchronize this data automatically. And this allows us to have a hybrid behavior. Obviously, the performance is not the best. And the case I present after, we took care of having the entire chain of execution taking place on the GPU. But it can help on some simulations if there is like one function or two functions that are not ported to GPU yet. Eventually, this work was enough to accelerate a fair share of the function of trust. But so now we could move a bit to the step further of optimizing the kernels. And well, this is not specific to Kokkos. This is actually generic to any GPU programming model, but optimizing kernels for code that was initially designed for CPU, you can imagine that it is a tough process because the code has a very CPU-centered logic, right? It has long kernels of sometimes hundreds of lines of code, many ifs inside, many branchings. You can use temporary arrays that don't play nice on GPU, especially on the registers. So the idea of optimization is to try to leverage all those difficulties. We also witnessed that there is a high sensitivity of the optimization against several GPUs, meaning that if you do an optimization for and you try it on two different GPUs of the same vendors, you may have very different behavior, performance outcomes of this optimization. If you move to GPUs of different generations, the difference increases. And if you compare GPUs of different vendors, not necessarily the same generations, again, you will have very high sensitivity on your optimization, which makes the optimization even more complicated. To give a bit more technical details, we still use a layout for our multidimensional arrays on GPU when the left layout would theoretically more suited. And we currently don't have cells reordering, meaning that we have for an unstructured solver a bad cache usage. So this is stuff that we are currently working. To give an idea of the evolution of performance over time over the different evolutions of the acceleration of trust. Here you have a graph that shows the execution time of one kernel. It's Navier-Stokes convective term kernel, tested for different steps of acceleration of the program. It was tested on NVIDIA ACE 6000 GPU on a case of 2.6 million cells. Initially, when the code was on using OpenMP targets, the kernel was executed on average on like 55 milliseconds. When we added Kokkos with OpenMP targets still around, it increased the execution time, and eventually by, optimizing the kernels, removing the OpenMP target code, and going further down in optimization, we could eventually obtain a code which is much more efficient than what we got before. You may ask, okay, but what if you didn't move to Kokkos and just kept using OpenMP target? You would just have the best results. Yeah, sure. But the thing is, OpenMP target was also bringing its own set of problems, especially data locality. We couldn't know. It was a bit difficult to know where the data was the most updated, whether on GPU or on CPU, and how to manage the transfer safely. Eventually, it was, the implementation that we took for that eventually played against us. So yeah, I would like to take the time remaining to present some consequent simulation that were run on GPU. So simulation that could run on CPU and that did run on CPU for some, but that would take much more time, would be impractical to run on CPU. Before that, I just need to define two performance metrics. Very low-level speed up, which is just the ratio of the execution time, of the wall clock execution time, and the performance per power, which take also into consideration the number of CPUs or GPUs, and the performance, the electrical power that was used during the computation. Unfortunately, since I didn't have access to the actual measured electrical power used during the simulation, I had to resort to using the theoretical value of the thermal design power, the TDP, which is less precise, but still gives an idea. So let's move to the first simulation, the meltdown incident simulation. So this is a work that was done by Elie Roumet during his PhD at CEA. So it analyzes the turbulent structures of a region of flow which is in contact with an exponentially heated surface. So this is obviously an unsteady simulation, and it uses the trio CFD Baltic, which is an extension of Kokkos that provides more turbulence models. In the context of a nuclear reactor, here we have the picture of the Osiris reactor of CEA. We perform a simulation with a Reynolds number of 20,000, a pressure of 10 bars. Characteristic time for heating is 5 milliseconds, meaning that at 25 milliseconds, we have reached the maximum heat. The thermal conductivity and the dynamic viscosity demands of the temperature, and the specific heat capacity is constant, which is a limitation of our models. The simulation is a hybrid between a DNS, so a direct numerical simulation, which means that we don't simulate the turbulence, we just have the full Navier-Stokes equations to simulate the flow close to the surface, and we move to a LES large eddy simulation away from the surface, because since we want to capture the turbulent vortices at the surface, we need to have a very small resolution. The smallest cells at the surface is of 1 micrometer, which satisfies the Batchelor and Kolmogorov resolutions. The cells have to be isotropic, meaning that the aspect ratio should be close to 1. So that means we have to refine also in the X dimension. So eventually we have a mesh of tetras of a very, I don't have the number of cells in front of me for the simulation. We use a finite volume element method for the numerical scheme, and we need, since we want to simulate 25 milliseconds of simulation, we need to perform 312,000 time steps, each of 80 nanoseconds. So this is due to the very small size of the cells. So such a fine-grained simulation allows us to have very precise and definite resolutions. Here you have the temperature fields a bit above the heated surface, both at the end of the simulation. But well, I'm not here to discuss about the physics. I'm not much an expert about this domain, but more about the performance of the computation. And here, initially, the simulation was supposed to be executed on 8,000 Intel Skylake CPU cores, which is about 300 CPUs, and it was performing at about 30 seconds for one iteration, which eventually would be estimated to last 3 months of simulation, which was way too long for the PhD students. So eventually he contacted the trust team and we could accelerate the remaining kernels that were needed, and we could run the simulation this time on 64 NVIDIA A100 GPUs, which was running at 9 seconds for one iteration. Eventually, it ran in 1 month. It was, well, if you do the performance, if you apply the performance metrics, about 3 times faster. But more interestingly, the performance per power that we get for between two simulations is of 7, about 0.5, plus minus 2. Means that the simulation with the NVIDIA GPUs was about 7 times more efficient, I would say, than the CPU simulation. And the reason is simple, is that we replaced about 300 CPUs, meaning 300 nodes in a supercomputer, by 64 GPUs, which is roughly equivalent to, say, it depends how many GPU cards you have, but like 32 or even 16 nodes. So eventually we use much less hardware in this simulation. So the benefit in electrical consumption is clearly visible. The second simulation I want to show is the flow-real reactor. So it's a work that has been done by Pierre Ledac. It's the CFD simulation of the flow within a test reactor, the test section of the flow-real reactor that you have seen on the picture on the right. So it's a large AD simulation. It uses PETC, the PETC precondition conjugate gradient, and a multi-grid module named Hyper, I'm not sure exactly how to pronounce it, Boomerang. And it's a simulation that runs on 25 million of tetrahedra. So here you have two planes of the solution. I think the velocity field in the reactor. Eventually, this simulation that was initially run in 2021 on 512 AMD ROM CPU cores, which represent 8 CPUs. It was executed at the run of 6.8 seconds for one iteration. And the same computation with the preconditioner and the multi-grid approach was done in 2025, this time on 8 AMD MI250X GPUs. And it ran at the pace of 1.5 seconds for one iteration. And if you do if you apply the performance metric, so we run about 4 times faster on AMD GPU. But the performance per power is much lower compared to the other case. It's only 1.5 here. And the reason is simple. We just replace 8 CPUs, but by 8 GPUs, because the AMD ROM CPU cores have like 64 cores per GPU, so they're already pretty massive. So eventually, in terms of amount of hardware that we're using, it's about the same. So that explains why eventually we perform a bit similar energy for the two simulations. Okay, I think it's time to conclude on this presentation. So Trust was ported to GPU using a mix of GPU libraries for linear servers and Kokkos for our own kernels, for our own logics and code. There is still a lot of work to make the code more Kokkos-esque, I would say, and also more efficient on GPU. But with Kokkos, Trust can run on CPU as before, and on NVIDIA GPUs and AMD GPUs with the same code. And this allows us to achieve good performance on simulations compared to CPU computations, and also good performance per power compared to CPU computations. And I think nowadays it is something which is even more important, maybe than just the raw performance. Okay, that's all for me. Thank you a lot for your attention.
Okay, thank you, Paul, for the presentation. So I will start with the question in the chat. So we have a question by Henri Pierre for Yuichi, I believe. Is there runtime optimization in Kokkos FFT based on data size, similar to the FFTW runtime planner?
Well, it's basically we are just interfacing to libraries, and at least in the QFFT and RockFFT has the just-in-time compilation optimization capability, and they are doing the same thing for FFTW. I'm less confident in the 1MKL, but other than that, I think we have the runtime optimization using just-in-time computation.
Okay. Little question also from Loic in the chat. What do you mean by right layout?
So this is how you order when you have multidimensional array. Well, you know that the memory in the system is just linear, it's just 1D. But when you want to have multidimensional data, you have to specify, okay, do you using a row column major or row major or column major is how you organize your data. And there is the right layout is more efficient on CPU, the way the data is accessed, because you can cache the next chunk of memory you will access. And the left layout is, or Fortran order also, it was named before. It's more suited for GPU because the memory is accessed by, say, by threaded fashion, and you can coalesce your data when you have a left layout.
Okay, so to summarize, the right layout, it's row-wise, it's C style, C++ style, and left layout is column-wise, it's more Fortran style. So if you are used to this kind of naming, because of course it's not exactly the same naming convention as all the software, so it's nice to have a little dictionary to be sure that you are mentioning the right stuff. Okay, so I will not have any more question in the chat, but I'm pretty sure there will be at some point, so I will switch to my question. So I will start with Yuichi. Of course, we will do everything in the same order. So I will start simply. You presented on the Fourier transform. You define your plans as in every kind of Fourier transform software. Can you support non-trivial Fourier transform if you have a non-uniform plan, stuff like this? Can you use custom plan if you need them?
No, because for the moment we are only interfacing to their well-established vendor libraries like K50 or Rocket50, and they do not offer that capability, so we can't for the moment.
But it will come at some point?
I personally I'm not interested in the non-uniformity, but I'm more interested in some feature. Some of them can come, but at least in the year it's in the long term plan at best.
Okay.
Just a brief idea is that in the year, if it is not covered by vendor, it's less likely to come. If it's covered by vendor, it's likely to come. This is the criteria.
Okay. So yeah, if you really need a non-uniform plan, you are stuck. You are obliged to do it yourself. That's a bit sad, but okay. So yeah, it's a question related to this one. So you insist once you use Kokkos A50 to have periodic boundaries to be sure that everything is okay. Is it only for performances, or is it really needed to make sure that everything is working?
If you like to use A50, it's most likely the periodicity is, but not necessarily, but I think in the because it is the most fundamental use case for A50, because periodicity allows us to construct the 50 basis and the 40 basis, and so but you can always use it for whatever purpose, but in the at least for simulations, it's more like the natural use case. But you can use just like if you try to analyze signals, and you can use it, of course. But for simulations, the most likely case is just periodic boundary. That's all.
Okay. Oh, we have a question from Loic. So thanks. Speaking of Fortran order, how easy it is to integrate Kokkos in the Fortran code base?
So yeah, that's quite a question. I was asked this question before, so I have something like a cheat sheet to answer you. But there is no per se direct support of Fortran from within Kokkos. Kokkos is a C++ library that use templates, etc. Fortran doesn't have something which is similar in its features. What the Kokkos environment, the Kokkos community provides you is a Kokkos Fortran enter OP library, which is also named FLCL. So the idea is that you write the parallel loops in C++ Kokkos in one file, and you create a Fortran interface, and you use this library to communicate between Kokkos and your Fortran code. You call actually this kernel that you've written in Kokkos from Fortran. This is not, say, super convenient to use, but well, it works. You're not the only one to worry about how to use Kokkos with Fortran. There is different initiative that exist. I know that in RIKEN, so the computing centers in Japan, there is an initiative to automatize the process using their Omni compiler that creates the necessary interface from part of the code that you would have tagged with specific comments. But there is still a lot of work to make it completely workable. I know, maybe Yuichi, you're a bit more knowledgeable about this than me. There is also the MLIR idea, so multi-level intermediate representation. So within the LLVM projects, you can use MLIR to go from one language to the other. You can use high-level operations. For instance, matrix multiplication is something you can express in MLIR in just one command. So the idea is from Kokkos code, you go to MLIR and you generate. The other way. No. For Fortran code, you generate MLIR and you generate Kokkos code, and so you can use it. But Yuichi, maybe correct me if I'm wrong. I don't know exactly what development is.
And that kind of development is made by, I think, Lawrence Livermore Laboratory, and it's not they have developed their own Kokkos wrapper. I don't remember Rokkos. If I remember the name. And the idea is, that Paul explained, just in their making their intermediate representation, and I think it's Fortran direct. But they do not necessarily use MLIR framework, but using this IR and to translate by their own framework to make their own Kokkos representation. It is on top of Kokkos, so it's slightly probably simpler, but in there they have some activities in doing that. But it's kind of private source code, so we don't have an access for the moment.
Yeah, and I would say the fifth option, the fourth option that you get is, well, something which is a bit trendy. Use AI and LLMs to translate your Fortran code to Kokkos. But yeah, I know there is a lot of effort on this, on the American national laboratories.
Okay, question from Mark. Loic is happy already. Question for Mark. So for Paul, you have unstructured data, so probably indirection to address to some cells, but you have good performances on GPUs. Is it mainly due to gain in the linear solver section? Thanks for the return of your experience.
I would like to give you more performance data. Unfortunately, I don't have such. For instance, I cannot give you, I would like to have a roof line to show, to give you, how much of the performance peak I have, or much of or close to the bandwidth, to the maximum bandwidth I am. We are all the code, which is common to unstructured solvers. We are not compute bound. We are just memory bound, meaning that we cannot fetch enough data from the memory, from the bus to compute. I mean, we cannot. We use too few data for the amount of computation that we do. If I phrase it correctly.
You mean because you have too much cells to compute, or they are too small?
Because we have many, as the question said, we have many indirections, obviously. We are unstructured, that means that we don't fetch the memory efficiently. There is a lot of cells when we load the memory in an interleave fashion. There is a lot of cells we don't need, because this is not the one that we need for now. We don't use the cache very efficiently. So I cannot tell you, we are performing this good for a given GPU, unfortunately. Well, the results that we have are okay, but for sure we are not making 100% of the GPU capacity. I know that, and for other reasons also, we don't have a very high occupancy on the GPU, because our kernels usually are pretty big. We use too many registers, and we try many strategies to either split the kernels or use the registers more efficiently. There is many reasons that makes us not being, 100% efficient for a given GPU. But you say you have good performance on GPUs. Yeah, we have okay-ish performance.
And I had a small question related to that. Why do you use triangle cells and not squares? Is it for precision?
I would say this is more for historic reasons. I know that. I think this is the part where I'm less confident, because this is the history of the code. But I think the team has more experience on tetrahedra rather than hexahedra. And we have some, by instance, I was talking about the volume finite element approach. So it's I think it is ported to GPU, but the same finite volume element method is not ported for the hexahedra meshes.
Okay. But maybe it will come at some point?
I was told that it's pretty difficult.
Yeah, of course.
Don't ask me why, but I was told that there was some effort to investigate how much work that would be to port also this part.
Of course, I don't ask you to implement that for next week, but...
No, right now, live coding.
Yeah, for this afternoon, if you have a bit of time, just after lunch. Yeah, of course. Maybe we will move to FFTs again. So you speak a lot about stream data or batch data. So if you batch your computing, is it the same behavior as you can batch, for example, for QFFT? Once you have a big amount of data and you say, okay, I want to perform this amount of FFTs on this big data and everything is scheduled and you don't have to worry about? Can you use it that way?
I mean, it's QA50 fundamentally supports this kind of batch capability by QA50 from any capability, and we are just using that API, which means that in there it's handled by QA50 completely. Just in there, we are extending this for the distributed prod, so you can pass the batched data to the our API, and we will use the internally this batched API QA50.
Okay. Oh yeah, you were talking once you have data on the CPU and you call a kernel on the GPU, then Kokkos will tell you, oh no, it's not coherent. Can we imagine at some point to have an automatic data transfer like the thrust universal vector, stuff like this, to handle this kind of not mistakes normally, because sometimes you can say, okay, it's really small, I can use an automatic transfer. Or do you prefer to explicitly transfer each time to be sure that the developer does what he wanted and not something with a mistake?
Yeah, we're only assuming that in the our input is the Kokkos execution space and the Kokkos views, and the Kokkos execution space specifies where the operation happens. So if you give the device parameter for that, we assume FFT was on device. In that case, Kokkos views must have the data on device already. If you give the data on host, it will give the compilation error. So it's safe to use.
Okay, risk for safety. So you are not allowed to guess if you have to transfer or not. If there is no transfer, you have an error and you have to fix it. Okay.
I would like to extend the answer of Suichi, but for Kokkos in general. So the idea, it's a philosophy in Kokkos that you don't have implicit memory transfers, because if you there is nothing worse than having a memory transfer which takes time, okay, which occupies your bus when you don't want to make one. You can use, we are talking about UVMs and share space. In Kokkos, you can create a view on memory space which is named the shared space. So it actually uses UVM and what is named for the other non-NVIDIA vendors. But when you do that, so that means that you don't control explicitly the memory movement, and it's left to the operating system and the driver to decide when you will transfer the data. It's very convenient, and actually during the Grace Code we will talk about this memory space, because it's very easy to make your code portable on GPU, but you don't have control on actually what is going on the data transfers. You may have data transfers which are not very efficient because it doesn't work on the whole, on the view as a whole, but as pages by pages. You try to access the data on the CPU, you get a page fault, and then you fetch the data, and etc. etc. So it's interesting, but at a performance cost.
Yeah, if you have a lot of data, it's not really efficient, but for small tables or kernel or convolution kernel, stuff like this, it's okay.
Yeah. But I'm more thinking about large kernels actually, and the tests we done, if I'm not wrong, are more targeted like large kernels. Large arrays.
Yeah, for large arrays, it's not a good idea.
Yeah. Having the entire application that runs like that. I mean, when you do only one memory transfers at the beginning and one at the end, well, it's fine because your memory never change location. But if you do a lot of data back and forth, well, it's a bit it's more in the philosophy to explicit your transfers all the time. When you want to
it's more clear,
it's more clear. And in the Kokkos API, when you want to do a memory transfer, you use a function which is named deep copy. It really means what it does, and you don't have hidden deep copy calls somewhere in some functions to make it everything crystal clear.
Yeah, in fact, there is another point if you use a default and the default is changing, you change the behavior of your program, but you don't know why, because it's just the default has changed.
When you mean a default, what do you?
Yeah, for example, I'm lazy, so I want to have automatic transfer, and it's working and it's nice. And at some point, I don't know, there is a update, and the automatic transfer does not work as expected, and I kill my performances, but I did nothing. So
yeah, you may have surprise.
That's strange. Yeah,
and you don't have control. Yeah.
So it's better. Yeah, it's better to have control. So Mark is happy. Okay. Oh, maybe. Yeah, we will switch to Paul. So you mentioned that the software was started in 1993. So it's quite a long time ago. So So of course the MPI implementation came well later, because as Joel reminded us in his if presentation, the very first CPUs which was capable to vectorize, not several, not parallelize, but vectorize, was in released in 1994, so 1 year after. So it was really a long time ago. But once you start to use a program which is really designed for one core, because of course at this time it was not much, and without vectorization, how do you manage, and what is the strategy to try to use MPI on it to parallelize everything? How do you proceed?
I know that the work, the MPI communication design of trusts has been done in 2006 something, so way before I came to CEA. So I'm not sure I can answer right fully. However, yeah, the project started in 93, but it's not a time capsule of 93. In 30 years, it went to many evolutions, going to vectorial machines, going to parallel, now going to GPU. So the job of the team is also to make the code run, to make it run on modern, or at that time, modern hardware.
Yeah, so you have to iterate, of course.
Yes. Yeah. And each time there is a new machine, it's okay. What is the compiler that we should use? Let's do some benchmark. Let's see how it's good or it's not good. How we can improve. Check with the engineers of the vendor of the machine. What are the good practices? Yeah, that's. But I think that's the same for many codes as well.
Yeah, but since you are talking about trust, it's nice to have a feedback on it, because everyone who has a code on CPU, want to port it on GPU, or to have to parallelize it, will dive into this kind of consideration. So it's nice to have a feedback. And yeah, maybe last question for you, and then we will move to Yuichi. When you port Thrust on GPU, do you keep always the CPU implementation, or do you consider that GPU is a must for the computing because it's really heavy computing and you don't want to wait too much and say, okay, I don't want CPU anymore? How do you decide?
It's an interesting question, because as I said before, Trust is used from very small simulations that just runs in a couple of minutes to simulation that last months. And for those consequence simulations, yeah, for sure. And that's what I showed, 2 simulations I showed. There are consequence simulations on billion cells. And we want to run them on GPU, on multiple GPUs even, to compute it in usable time. But on the other end of the spectrum, and maybe I didn't emphasize that part enough, but we have very small simulations for those running on GPU is just nonsense, because you will just spend so much time just moving the data around, and say starting a kernel on GPU is not instant. There is a small time needed for that. When
you have a latency.
Yeah, we have a latency. When you have consequent execution of time for your kernel, it doesn't matter. But when your kernel is so small, I mean, the data it manages, the computation is so small, well, it doesn't make sense. So for small simulation, I think the sweet spot is, if I'm not wrong, less than 1 million cells. It's preferable to execute it on CPU. we run Trust sometimes on just single nodes, just on one CPU core without MPI activated. And so it was important for us to keep one implementation, right? We didn't have to have like the kernels duplicated between the CPU and the GPU version. And with Kokkos, we can achieve that because we write the code in Kokkos, okay? And depending on which backend we select, we can compile it for GPU or for serial CPU. So we keep eventually only one code base, which is in Kokkos.
Yeah, and then Kokkos does the rest for you. And
Yes.
if you want to change the target, it's up to you.
But
Okay.
it led to interesting performance analysis of running Kokkos with very small kernels and very small data, and the latency, because you have when you start a kernel, there is a latency on GPU, okay, but which is due to the how CUDA starts a kernel on the GPU, but also you have the latency due to Kokkos because of the internals of Kokkos that you are calling, and it's very negligible on large execution, but for very small execution, like executing a kernel on 1,000 elements, then from Trust we raised some issues about but the time to run, it's not even a kernel because it's just like a serial loop that we are running on the CPU. The amount of time we spend in the Kokkos functions is too high. So eventually it led to some optimization. We realized that there was in Kokkos some, since it was not that much in the scope of Kokkos, there was some things that could be optimized in that domain.
In fact, it's quite common. Even in CUDA, if you want to compute on 1,000 elements, it's way too small for a GPU. So of course, the data transfer will be huge. The kernel will be so small that you have to zoom forever on inside to see it. Yeah. And then we see, okay, I have 1 second of computing, but in this 1 second, I have 0.1 millisecond of kernel. So, yeah.
But here, I mean, especially running on CPU with a serial backend, so no GPU involved. It's just that the mechanism of Kokkos from your parallel 4 to the very beginning of the kernel, which is just serial.
You still have a little overhead, and some point could be quite annoying. Okay,
I remember
now it's fixed.
Yeah, it's fixed. There was a string that was involved at some point. We were constructing a string that was not necessary, and the time of constructing this string was significant compared with the execution of the loop. By instance, that's just one example. So we are at this kind of level. It's I think it's nanoseconds that we want to save at this scale.
Yeah, but if you call the kernel a lot, it counts.
Yeah, it does. And it was a good opportunity to shed some light on this kind of use of Kokkos.
Okay, so I still have some question for you, but I will switch to Yoshi a bit. You presented a lot of distributed computation. So you can use MPI, you can use Nickel, you can use a lot of stuff. And of course, you have a problem of scalability. Because all to all is not really scalable, of course, by definition. And so you plan, as you mentioned, you plan to use NVSHMEM, not OpenSHMEM at some point also, or you want to use only NVSHMEM? For the GPU is better, but you can use OpenSHMEM also for the CPU parallelization.
I don't know about the OpenSHMEM, just in the NVSHMEM is certainly the better option for all communication and NVIDIA GPUs.
In fact, NVSHMEM is based on OpenSHMEM. So
I mean, I don't, because it is for CPUs and we don't necessarily know, and it's outperforms or MPI, and frankly speaking, and our focus is more like on GPUs and the optimization there, CPU backend is kind of secondary important task, and it's not the first priority for us. And probably we can try in the future, but we first need to finish the GPU optimization. We can try after that.
And maybe you can use also another point. I think it was last year DK presented in the GTC an optimization for all-to-all communication, because a lot of people are using all-to-all communication, even if it's not scalable. And inside NVAPISH 2, they implement an optimization while you are doing an all-to-all communication. You have extra thread to do some computing to be sure that you still compute, because the big problem of an all-to-all operation is you stop everyone, you communicate, and during this communication you have no computing at all. And that's a big problem, especially if you have a lot of cores, of course. And they did this trick inside NVAPISH to be sure that once you are using all-to-all, you still use the computing at the same time. So is it a trick that you could use also to optimize the collective MPI, stuff like this?
You mean the internal FFT operations for the moment? Not, but technically we can do that because we have the batch capability, and the batch direction can be independent. So we can do some overlapping. The thing is that in there, it's probably super important optimization for CPUs, but on GPUs, the computation cost is quite negligible, and even if we do some overlapping, it doesn't help entire performance. So alternatively, we can consider the callback capability to feed additional computational kernels, which can be executed at the same time with our FFT operations involving communications. That's my consideration.
Yeah. Okay. Oh yeah, another question for Paul. So you said that historically the first was developed with the CPU logic, so there are a lot of reallocation inside the kernel, and of course allocation costs a lot on a CPU and on a GPU, of course, because it's not free. And you dive into the quite common path, in fact, once you want to optimize or port a code on GPU, that you have to optimize already for the CPU. So getting rid of this reallocation to use maybe some temporarily that leave for all the simulation, and then going back on GPU. Is it that what was done to port first?
I
or?
don't have, feedback on reallocation within the kernels. I'm not aware that this is something that we do a lot. So I'm not sure. I'm not.
It could happen. It could happen for the first version, but normally should disappear at some point.
For this, I'm sorry, I cannot answer. I'm not sure.
Or maybe for the school, you keep that in mind for the school.
Yeah, I can. Okay, I can ask my colleagues. And
because it's really interesting for all the people watching the school and having a historical code base and trying to figure out how to do to optimize it. So it's nice to have feedback.
There is many things that you can do on CPU, which is okay, and you cannot do that on GPU. It's much more costly. It's much more inconvenient, for sure. And usually going to GPU, I like to say that it forces you to solve your technical debt and to clean up your code, to clean up how your loops, your space loops are implemented.
And maybe related to that, do you use streams once you are doing some?
You mean asynchronous execution?
Yeah, asynchronous execution. So you can also have asynchronous transfer, asynchronous kernels, asynchronous free, also an allocation you can. So can mitigate your problem maybe at some point.
Indeed, no, that's not something we are doing. That's something that we want to investigate. We wanted to investigate in several ways, just using streams, but also using the graph, the Kokkos graph API.
Yeah.
We did some experiment at some point about that. It's for now it's not streamlined. We got some difficulties, I would say. Yeah, we did experiment, but I'm not sure we're gonna push it for now to the code for the way it is.
Yeah, of course, it depends on the kernel. And as Stephen Jones reminded us during the GTC this year, it's a parallelism by opportunity. So if you consume too much resources on one kernel, maybe the other one does not fit at the same time, and you are stuck.
I would say for small, for simulation where we don't fill the GPU memory completely, it's interesting to have asynchronous execution. But since we really try to pack, the GPU with as much data as we want to
can
just run the simulation of as few GPUs as we can. So it's that's more work that one of my colleagues tried. There is not that much benefit of using asynchronous in this case.
Yeah, because of course
we already fill the entire GPU with one kernel. So if you want to have two kernels running at the same time, it's just not efficient.
Yeah, so at least you can maybe do some transfer and compute at the same time, but maybe not two kernels at the same. So maybe graph is not a good option for you, or at least for this particular example. Maybe,
but the Kokkos graph approach is very close to the CUDA graph approach. So it's not based on data flow, but instead in Sycl, the graph is based on where you need the data and when, which is interesting because you can make graph pretty easily. For Kokkos, it's more like I have this task I want to run on this, and this task I want to run on this, and dependency between tasks. So maybe I should. That's something we want to consider a bit more. I think the data transfer is something like high the data transfers is something that we want to achieve to some point.
But maybe again, sometimes it's not worth it because you have really big kernels, and if your kernel is computing for hours, you don't care the data transfer. So always a trade-off. You have to play with it again every time. I have a question for both of you. Do you manage NUMA on your simulations, on FFTA and on Trust?
I would say for Trust, I don't think we have any specific mechanism for that.
Well, for me, I'm just using the OpenMP setting for CPUs to make binding closer, but that's all, and I didn't explicitly use the NUMA control.
Okay. And since you mentioned you have a lot of indirection, maybe at some point you can have a problem with, at least on CPU, if you have a NUMA node, because of course you will have a big penalty on the access if you are not on the right border on the NUMA data.
For that I'm not aware of.
Okay, so I think we're on time. Says I just check quickly about your 512 CPU cores, Paul, versus the 8 MI250X GPUs.
Yes.
I don't know the datasheet by heart, of course, because it's the job of Adrien to follow AMD stuff. I follow myself. I follow more NVIDIA stuff, and David is following Intel stuff. But it seems that one MI250X has 14,000 cores. Of course, it's GPU cores, so they are really small, but you are comparing 512 cores CPUs to 14,000 cores by 8. So of course, it's not really fair to say that because one GPU core is much smaller, but maybe
the same kind of cores.
I don't have the number of 3 processor there is in this card. But it could be interesting to have also the number of multiprocessors or number of computing units, they call in AMD, to compare, and not only the number of GPU, because of course the GPU is maybe something like 9 pounds or something like that, so it's not fair to compare that to a single CPU, even if you have 8 CPU.
But it's always a difficult question comparing the performance of CPU and GPU, because
it does. It is.
You sometimes you see crazy speed ups that just don't mean anything. I tried. I think using the raw speed up it doesn't tell you all the story. it's very limited. So using the performance per power is a bit more indicative because you take into consideration how many CPUs/GPUs that you're using. Another matrix, but I couldn't apply it for those cases, is you try to use the best CPU and GPU simulations, okay, that you can get, the best configuration for CPU, the best configuration for GPU, and you try to compare them and apply those performance metrics. It's a bit more fair in comparison.
Yeah, and for you, normally it's much more simpler because you can ask Kokkos to compute on CPU only and then on GPU, and then you can compare. You don't have to redo the work to be sure that it's possible. Of course, you have a little overhead, as you mentioned, but you can fix it, and it's only for really small kernels. But to compare and to have a nice idea what's going on, it's a good point. Yeah. Okay, so I'm out of question. So I think we'll finish on time today. So thank you everyone for coming here today. Thank you, Yushi and Paul, for the nice presentation, all the answers, all the stuff you mentioned here. So of course we will have more details about how to use Kokkos with the grayscale direction, with all the wizardry that we can have on GPU and on CPU. So for the school. So if you want to register, especially if you want to go in Nancy, we will close registration tomorrow. So if you really want to attend the school in Nancy, that's your last chance today and maybe tomorrow morning, but that's it after that. So Mary is sending you all the link in the chat if you want to have a look. Next week, we will do some wizardry with Rust, because at some point, a lot of people want to do some Rust. So we will have a nice webinar, really long webinar on Rust, so to introduce the language, to introduce what we can do with it, and to have also a bit of history, because, of course, this language came with a certain idea in mind. So it's nice to have all the history in mind to enjoy the whole story. So don't forget this webinar. That being said, thanks for joining us today and see you next week. Bye.
Thank you, everybody.
Bye.
Goodbye.